Good morning, everyone. Today we are going to learn about nature of light as particle. Let's look at these two pictures here. We have molten lava, which is emitting out a color, and we also have a substance which is melted, and this melted substance is also emitting out color. The wave nature of light does not explain how an object can glow when its temperature increases. So that's what we saw. The wave nature is not able to explain why this object is glowing when its temperature increases. The explanation to this was given to us by Max Planck, and according to him, uh, energy comes in packets called quanta. So he was the first one to give us the word quantum or quanta, and we will learn about this word a little later on with quantum mechanical model when we will be studying about electrons in detail. Max Planck, through his experiments, hypothesized that electromagnetic radiation was given off by vibrating atoms. He proposed that each atom vibrated at a fundamental frequency and therefore emits radiation of certain energies. He also provided us with the relationship between energy and frequency. So this E is for energy, H is a Planck's constant, and this is nu. Nu is for frequency. And according to this equation, if the frequency increases, energy increases. And if energy decreases, frequency also decreases. Therefore, giving us a relationship between energy and frequency that they are directly related to each other. As one increases, the other one also increases. Let's discuss about this H. H is a Planck's constant, and the value for Planck's constant is 6.626 times 10 to the power of negative 34 joule second. This is a constant value, and you will always be provided with this constant value. You do not have to memorize it. Okay, so Max Planck discovery was a very shocking discovery for everyone because up till now, everyone thought light as a wave, and light has wave-like properties with wavelength, some frequency, and amplitude. But Planck's discovery that energy is not continuous but is quantized, meaning that it can only be transferred in individual packets, was very revolutionary. While this might sound a little confusing to us, we are actually familiar with quantized systems. The money we use daily, for example, is quantized. For instance, when you go into a store, you will not see anything on sale for a price of $1.02. This is because the smallest possible monetary unit is a penny. It is impossible to transfer money in any smaller amount than a penny. Just as we cannot pay the cashier at the store half of a cent, energy cannot be transferred in anything less than a single quantum. We can think of quanta as being like pennies of electromagnetic energy, the smallest possible unit by which such energy can be transferred. So Planck's discovery that electromagnetic radiation is quantized forever changed the idea that light behaves purely as a wave. In actuality, light seemed to have both wave like and particle like properties. Albert Einstein took Max Planck's work. He did a few experiments of his own and came up with this photoelectric effect. Photoelectric effect refers to the emission of electrons from a metal when light shines on the metal. So let's look at this picture here. We have a wavelength of light which is shining on this metal surface, and when this light shines, electrons are emitted out of that metal. So electromagnetic radiation strikes the surface of the metal, ejecting electrons from the metal and causing an electric current. And this was proved by Albert Einstein in his photoelectric effect experiment. He was awarded a Nobel Prize for his experiment. Albert Einstein also gave us this term which is known as photon. Photo comes from the word light. Photo means light. A photon is a particle of electromagnetic radiation. It has no mass to it, but it does carry a quantum of energy. So photoelectric effect provided us with the evidence that light can behave as a particle. So let's look at this picture here. This is sodium metal, and we have these atoms, sodium atoms, and there are two types of light which are shining on this metal surface. The first one is the red light, and the second one is a violet light. We see that the red light is not able to eject out electrons, whereas the violet light is able to eject out the electrons. There's a difference between these two. The properties are a little different. We have the red light with a longer wavelength and therefore smaller or less frequency, and violet light has a shorter wavelength with more frequency. So electrons will only be ejected once the threshold frequency is reached. And in this case, the threshold frequency was reached by violet light, not by red light. So below the threshold frequency, no electrons are ejected, and above the threshold frequency, the number of electrons ejected depend on the intensity of light. And intensity of light depends on the amplitude of the wave. Okay, let's look at some of the examples on how to use the Planck's equation to solve these questions. Question 1 is to calculate the energy of a photon of light with a frequency of 7.30 times 10 to the power of 15 hertz. So we are given in the question frequency, which is 7.030 times 10 to the power of 15 hertz. Our unknown in the question is energy. We have to calculate energy. We know that this is the equation that we need to use because we have frequency. We know the value of Planck's constant, and now we can calculate energy. We just need to plug in the values of Planck's constant and the frequency and calculate energy. And the final answer for this question is 4.84 times 10 to the power of negative 18 joules. Now let's look at the next question. Question 2. Calculate the energy of red light with a wavelength of 720 nanometers. This is question 2 for us. We are given the wavelength, which is 720 nanometers. Our unknown is to calculate energy, and the unit for energy is joules. We know that 1 meter is equal to 10 to the power of 9 nanometers. We know that this is a wave equation. Speed of light is equal to wavelength times frequency. We also know the Planck equation. Energy is equal to Planck constant times frequency. These are the two constant values that you will always be provided with. You do not have to memorize these values. C is equal to 3.00 times 10 to the power of 8 meters per second, and H is equal to 6.626 times 10 to the power of negative 34 joules second. We're going to start with the wave equation because we are given wavelength in the question and we need to calculate frequency for us to know the value of energy. So we're going to rearrange this equation, the wave equation, this way for us to calculate frequency. So frequency is equal to speed of light over wavelength. But wavelength is given to us in nanometers. Our first step is to convert nanometers into meters using this conversion factor. Once we have converted that, we can plug in the value into this equation and calculate frequency. Now, once we have the value of frequency, we can come back to the Planck equation and plug in the values of frequency and Planck constant to calculate energy. The final answer for this question is 2.8 times 10 to the power of negative 19 joules. Now let's look at the last question. The last question, question 3, is to calculate the wavelength of a photon with an energy value of 4.93 times 10 to the power of negative 19 joules. We are given energy in this question, the value of energy, which is 4.93 times 10 to the power of negative 19 joules. Our unknown is wavelength. We have to calculate wavelength. These are the things that we know. We know the wave equation. We also know the Planck's equation. We know the value of C, and we also know the value of H. Since we are given energy, we are going to start with this equation, Planck's equation, and we're going to rearrange it to calculate frequency. We know the value of E, we know the value of H, we can calculate frequency. Once we have the value of frequency, we come back to the wave equation. Now we can calculate wavelength. We just have to rearrange this wave equation to calculate for wavelength. Once we have rearranged it, we just have to plug in the value of C, plug in the value of frequency, and calculate wavelength. The final answer is 4.03 times 10 to the power of negative 7 meters. The question did not specify the unit of wavelength, so we can leave the question here. Like this is a good answer in meters. But if the question asks us to calculate in nanometers, we would have to convert this unit into nanometers, and a final answer would be 403 nanometers. That's it for today, guys. We will regroup for the next lesson. Please get back to me if you have any questions, and I will try to answer it as soon as possible.